Then I'm happy to deal with the first part, first application example of constraints, with this, which is a kinetic limitation between condensed phases. At the example of GTOx, our GTT internal oxide database, for a glass application example. A quick introduction of GTOx. What actually is GTOx? That is our in-house developed GTT oxide database. In close collaboration, it has been developed with our partner at Forschungszentrum Jülich. Current version is number 19, which gives you an impression already on the history of the database. So it has grown from an oxide-focused database in the first versions, now expanding the scope tremendously, covering so far 26 different elements, which means 26 elements. It contains binary, ternary, quaternary assessments whenever available of oxides, metals, phosphates, sulfides, sulfates, carbonates, chlorides, fluorides. So it's a quite extensive database by now after spending a lot of efforts in this. Three things I consider special about GTOx are that it relies on the associated species model, so it differs a bit from other oxide databases, which has implications also on the modeling options. The Calfedian among us could evaluate and judge a bit. For those who don't understand different Calford models, it's not super important for my talk here. What's nice is ever since the last version, we have a unified liquid description of the liquid phase covering a slag, so oxide, the matte phase, and a metallic melt, which gives the opportunity, for example, to describe in the iron, oxygen, sulfur phase diagram a metallic rich liquid phase here in the iron side. Continuously, you can increase the sulfur concentration to describe still with one liquid description also a more sulfide melt, or increasing the oxygen concentration with one liquid description. If that is not contained in one liquid description, you will have phase transformations by having separate liquid descriptions for a slag, for a matte phase and a metallic melt. So that is nice. And what's really special about GTOx is that the phase selection is very easy, because you can simply select all phases, and that is a safe bet when you are interested in full equilibrium. And we will discuss a bit why this is not always applicable and how to do that when you want to have more kinetic constraints. What is new in version 19, which is available in FactSage 19, is that we have added cobalt and lead, which are relevant for lead metallurgy and also for lithium-ion battery recycling, which is quite important nowadays because cobalt is quite rare and important, right? You want to recover it as good as possible. When I say these elements have been added, means typically that we have added it as a metal, as an oxide, maybe when there's multiple valency as cobalt, it has been added as two oxides, both stable oxides, or as a sulfide. We have done the unification, as I tried to explain beforehand, and we always add new assessments. We work on the existing ones. Whenever there's new data available, we find contradictions, we have indications that we can improve something, it will be improved, and we add more assessments. We have an increase in 10% of solid solution phases. We have an increase of 50% in stoichiometric compounds from one version to another, which is mainly related due to Cassie's excellent work in adding binary metal descriptions. So all metal binary interactions have been added in the process of having a liquid unification. So that was a tremendous increase also in scope. What we also did is to work with respect to physical properties, adding density data, machine learning informed density estimation for everything that is solid solutions, solid compounds, so stoichiometric phases, but also liquid phases for all end members, which gives you the opportunity, for example, to calculate the different densities for matte, slag, metal phase, and predict, for example, their demixing based on the different densities in a process, which is very valuable and very accurate if you see this application calculation or example calculations where we find some experimental densities and calculated ones, which trend-wise show a good agreement and allows for the prediction of their phase separation based on density. Now, what will be new is that we will add boron. Boron is particularly interesting for glass design, for glass applications, because boron is an important constituent in glasses. We have added more than 100 glass relevant systems, mainly Tanya did, in an excellent way. Binary metallic systems, quasi-binary boron oxide, metal oxide systems, as you can see here. So everything with boron here is light green, even though you cannot perfectly read the elements here. You can believe me that they all have been added. Also higher order systems have been added, and like this. That is the tedious but very important work on the binary ternary level to get high quality predictions to higher order systems. What we always do is to do multi-component calculations based on experimental data to really verify, to check the quality of our predictions as the core of the Calvert approach. What we also have put a lot of emphasis on is to describe the metastable or sometimes stable liquid miscibility gaps. These are the systems marked with an X, and I will show you some of these. So first of all, you can appreciate the great agreement between experimental data points and calculated phase diagram based on the work Tanya did. And what you also see is that these systems here, we can zoom in for one system, boron oxide, sodium oxide, for example, that you can see the metastable miscibility gap. That is not relevant when you are in full equilibrium. You do not need to care about this. You need to start caring about this when you're dealing, for example, with glasses, because then you have an undercooled liquid, and then you are highly interested in if your glass, when you undercool it, is demixing into two different liquids or not, because this will have a huge impact on the optical properties of your glasses. So, by including it in the modeling, you can use a database to, for example, do glass design and find out if that is a promising composition or if that composition is maybe prone to liquid dim phase separation that makes it much more less interesting for glass application. As you, for example, see here, right, where you can easily imagine that the optical properties are not so good. Now, Moritz's beloved mass valency constraint slide. We can do that same now for our binary system. And you would see here in SLIC, first of all, you see that it is one liquid description for the metallics, for oxides, some associates, more complex. You will see that in this system we have many stoichiometric solids. And what we want to do in that very simple scenario is suppress crystallization. We can simply kick out all solids. They shouldn't form, right? We want to calculate how the system evolves without allowing crystallization. Now, for full equilibrium, that is the easiest calculation you can imagine. You select all phases and then you're good to go. We are now in the phase diagram module because we want to reproduce a phase diagram as I've shown you before, which showed the interesting miscibility gap, which was metastable. If we now suppress crystallization, we see that we simply, as I pointed out, deselect all solids. We only have the liquid phase. We allow for phase separation by having the J option active, and then we get two completely different phase diagrams, right? And by superimposing these with the phase figure module, we see that we can reproduce what I've shown you before. It's a superimposition. That is what I've shown you. It was not a correct phase diagram, right? Because it includes also the metastable miscibility gap, which is very important. Now, we can ask ourselves on that very easy binary system, what would be the demixing temperature for phase separation of the liquid phase? For a certain composition, let's take 20 mole% of sodium oxide. That is easy to read directly from the phase diagram, right? 575 degrees C, which is an important quantity for a glass manufacturer to find that out. Now, technical glasses are often more complex chemically, but the demixing tendency very often originates from the binary underlying systems. So we can now maybe increase chemical complexity a bit, and we go for an arbitrary chosen composition with some silicon or silicon dioxide based, boron oxide, sodium oxide, potassium oxide, and we can still ask the same question. What would be the demixing temperature? At some point, when the chemical complexion is increasing, the phase diagram module is not very convenient, right? It's very difficult to compare or to show so many dimensions on a binary plot. So I would move to the Equilib module. We can again suppress solid phase formation, so we don't allow solids to form. We only have slick activated, but what we do is to do a temperature screening, and what is very important is to have transitions on. We want to exactly find the transition temperature for a second liquid phase to precipitate from the undercooled liquid, because we suppress crystallization. And by 1 second calculation, we directly get a result because it's an easy calculation, and we would see there has an additional calculation being performed compared to the discrete time steps, temperature steps we have enforced anyway, and that is at 617. We see also when we plot it, slick 2 starts to form. So in that case, we also know the demixing temperature, 617 degrees C for that more complex glass. And for example, like this, we could screen composition space. We might want to change the ChemApp for Python, do that in an efficient, automated manner. And like this, we already have gained valuable information. But there is more to consider. There are many different glass compositions, and I already indicated that we aim to verify that our binary and ternary assessments yield high quality extrapolations to higher order systems. So what we do, we check the literature, we check what experimental measurements have been done, and here you see a list of references. You see that we have investigated the liquid phase separation for silicon iron based glasses and silicon boron based glasses. And then we take one glass, one composition, different composition and temperatures, and what we can investigate for, let's say, one element for silicon, how the silicon concentration experiment differs compared to the calculated one. So red is full agreement, and then we see the silicon concentration between the different liquid mixtures upon phase separation, and then we can compare how well that is in line with the experiment. Trend-wise, you already see that this looks quite good. Sometimes quantitative agreement is better, but overall, this already looks quite promising. We would do that for different glasses. We would do that for different temperatures, different compositions, and different elements, of course. And then we see that the overall trend gives us a good impression about the quality of the database. Now, for all composition and conditions, a miscibility gap has been predicted, and also the elemental distributions is in quite a good agreement with the experiments. So this gives us some confidence in the database quality. Now, this was one example of the calculation of considering constraints. There is more that one could do, which is valuable for example, insights in how easy it is to produce a glass. When you have an undercooled liquid, you are highly interested in the driving force. Moritz has already explained that concept in the driving force for solidification, for example. So when you undercool it, if the driving force is very, very high for your glass, it's difficult to form a glass. If it's very low, it's very easy to form a glass, right? So it's a quantity you should be interested in. We could, for example, as one composition, we can again take our 20% more sodium oxide, 700 degrees C, so we ignore our miscibility gap now, and we want to ask what is our activity of the solid when we have an undercooled liquid, or all our solids. This driving force is a very important thermodynamic indicator for glass forming ability and a key ingredient for more advanced kinetic modeling. So we should know how to calculate it and how to apply it, for example, to construct TTT diagrams or some other kinetic models. On a theoretical perspective, what we aim to do. we have our Gibbs energy and we calculate our Gibbs energy for our liquid phase only. It might, for composition X, which is around 20%, might look like this, our tangent, our minimum Gibbs energy for liquid. And then we consider one stoichiometric compound being there as a dot, which is sodium, 1 times sodium oxide, 4 times boron oxide, it's 20%. And what we calculate is the equilibrium based on liquid only, and then we check the relative stability of that other stoichiometric solid phase in this case. So we shift our tangent down and see what is the driving force. So the driving force is our delta between these 2 points, and the driving force is connected to the activity with RT ln A. Here in this case, the solid is more stable, right? It would like to precipitate, and we can quantify that at every composition, at every temperature, at every condition. Here, another compound might be above, so it might have an activity smaller than 1, and then it would not like to precipitate. But we set them as dormant, right? By setting it at dormant, we calculate the relative stability of all these compounds, in this case, compared to our calculated equilibrium. How do we do that? We take, in this case, because solution phases here are not relevant, we take all pure solids and we add a lot of dormant phases just to be sure that we catch all of them. And then we do a point calculation, that very simple example, 700 degrees C, fixed composition. And what we get, for example, is that 3 solid phases would like to precipitate at 700 degrees C, which is expected, at least for one, where we can now quantify their activity, calculate their driving force, and use that for more advanced kinetic modeling if that is of interest. These were 2 examples. One can do much more. When it comes to glass ceramic application, for example, you could also calculate your equilibrium based on a solid, crystalline solid and your liquid phase, and then you can calculate, for example, what is the driving force for a second solid to precipitate. That is another very interesting application example, which I will not explain, but I want you to be aware that this is technically the same thing, the same principle applies, but is simply a type of calculation where you add in your equilibrium consideration then another solid phase. What I would want you to take away is that there is not the common notion, or there's often the common notion that FactSage and these calculations are full equilibrium only. That is not the case. One can get very important insights if you are not in equilibrium with these type of calculations. You just need to be aware what you're doing when you exclude phases and how you can use these insights. In addition, with the upcoming version of GTOx, you can do very accurate predictions of properties like liquidus temperature, which is standard, right? But also liquid phase segregation, simply by having these metastable miscibility gaps properly also modeled with the assessment, solid phase separation or precipitation and evaporation for complex multicomponent boron-containing glasses. Then there's more. One thing I haven't even discussed, but I want you to be aware of. For example, for the thin film lovers among us, vapor phase condensation can also be modeled, for example, this bit type of different concept. With the para equilibrium, it's a different setting in Equilib, but in these scenarios, for example, this gives very interesting results. And then there is a QA method that will be explained now by Anna, which is another way of approaching non-equilibrium and considering constraints. One final comment, because driving force is so hot as a topic. If you join our Calvert Optimizer course, you would learn, or you might have learned already, because I see some phases who have participated already, how this concept of dormant phases actually enables very robust one-shot optimizations with the Calvert Optimizer, because that was really a game changer in the performance of the tool when we started considering the driving forces. Thank you.